All right, so the actual last part of chapter 8 is complex numbers. So without further ado, let's learn about what the heck complex numbers even are. All right, so part 1, writing numbers in the form BI. In this section, we will be discussing a number system that includes the roots of negative numbers, something that you probably didn't even know existed until right now, which is cool. This number system is called the complex number system and includes the imaginary unit. Sounds exciting. The imaginary unit, written as I, is a number whose square is -1. So this is probably counterintuitive to anything you've ever learned about squares, but here we are. So we know that I squared is equal to -1, and therefore I is equal to the square root of -1. To write the square root of a negative number, in terms of I, use the following properties. So if we have the square root of -a, where a is just some number, we can break that into the square root of -1 times the square root of a. We know the square root of -1 now is I, so it would be I times the square root of a. So for instance, the square root of -16. We could break up into the square root of -1 times 16. Then our product rule tells us we can break that apart into the square root of -1 times the square root of 16. We know the square root of -1 now is I, and that the square root of 16 is 4. So we're going to get I times 4, which we're going to write as 4I. Okay. The product rule for radicals does not necessarily hold true for imaginary numbers. To multiply the square roots of negative numbers, first we write each number in terms of the imaginary unit I. So if we had the square root, for example, the square root of -4 times the square root of -9, we could not just go ahead and rewrite that as the square root of -4 times -9, which would be the square root of 36. Instead, we have to write that as the square root of -4 we know to be 2I, the square root of -9 we know to be 3I. 2I times 3I would be 6I squared. I squared is -1, so 6 times -1, which would be -6. Okay, so the product rule works a little bit differently now that we are dealing with complex numbers. Okay, so we're going to do a couple of examples. Number 1 says the square root of 8 times the square root of -2. So we're going to have to go ahead and first let's simplify the square root of 8. So we know square root of 8 is equal to square root of 4 times 2 equals square root of 4 times square root of 2 equals 2 square root of 2. And then the square root of -2 we can write as the square root of -1 times 2, which is the square root of -1 times the square root of 2, which is equal to I times the square root of 2. Okay, so our problem has become 2 square root of 2 times I square root of 2. And now, if we do a little bit of multiplication, that's going to be 2I times square root of 2 times square root of 2. If we're looking at square root of 2 times square root of 2, that's the same thing as square root of 2 quantity squared, which we know is just equal to 2. So we're going to have 2I times 2, which is going to be 2 times 2, which is 4 times I. So our final answer is going to be 4I there. Next up, we have the square root of -125 divided by the square root of 5. Square root of 125, we can go ahead and, of -125, we can go ahead and break up. We know that's going to be equal to the square root of -1 times 25, 50, 75, 100, 125 times 5 times 25. So square root of -1 times square root of 5 times square root of 25. Square root of 25 is 5, square root of -1 is I, so 5I square root of 5 is going to be our numerator. So we're going to have 5I square root of 5 divided by square root of 5. Square root of 5 divided by square root of 5 goes ahead and cancels for us. So our final answer is going to be 5I. And we can cancel those square roots of 5 because in our numerator we have 5I times the square root of 5. If this was 5I plus square root of 5 over square root of 5, we would not be able to cancel there. Remember, we can only cancel when we have multiplication. Okay, so now that we're familiar with using I, we can define complex numbers. So definition, a complex number is a number that can be written in the form of A plus BI, where A and B are real numbers. The set of real numbers is a subset of the complex numbers, since any real number can be written as a complex number. So that just means that the complex number the realm of complex numbers includes all real numbers, because we can write any real number as a complex number. For instance, 16 is equal to, we could rewrite that as 16 plus 0i. So technically we have written the number of 16. We have written the number 16 as a complex number. So we've taken a real number and written it as a complex number. So in general, complex number a plus bi is a real number if b equals 0, because 0 times I is just 0. So then you're essentially adding nothing and you're just left with your regular old number, real number. So another definition, a complex number is called a pure imaginary number if a equals 0 and b does not equal 0. So for instance, 3i is equal to 0 plus 3i. That's a purely imaginary number because it is attached to the imaginary unit I. So this brings us to adding or subtracting complex numbers. Two complex numbers can be added or subtracted by adding or subtracting their real parts and then adding and subtracting their imaginary parts. So the sum or difference of imaginary numbers. If a plus bi and c plus di are complex numbers, then their sum is going to be a plus c plus b plus d times I. And same thing with their difference, a minus c plus b minus d I. So for example, add or subtract complex numbers. So number one, we have 2 plus 3i plus negative 3 plus 2i. So we know that that is going to be equal to a plus c. So in this case, we have 2 plus negative 3 plus b plus d times I. So in this case, b is 3 plus 2i. So 2 minus 3, so plus negative is just going to give me a minus in there. So 2 minus 3, I'm going to erase that, put 2 minus 3 is negative 1, plus 3 plus 2 is 5 times I is 5i. So we're getting negative 1 plus 5i. So really you're just kind of plugging and chugging in that formula. Number two, we have 5i minus 1 minus I. We're just going to go ahead and distribute our negative in this. So we're going to have 5i minus 1 plus I. And so 5i plus 1i is going to be 6i minus 1, or negative 1 plus 6i. Number three, we have negative 3 minus 7i minus negative 6. So we can go ahead and make that negative 3 minus 7i minus negative is plus 6. And then basically you're just combining like the real number parts and then the imaginary number parts, right? So like negative 3 plus 6 is going to give me 3, and then minus 7i doesn't have anywhere to go. It just kind of stays there. Okay, so adding and subtracting complex numbers, not too bad. You basically just look at these formulas and remember that we kind of break them into real parts plus or minus imaginary parts. Multiplying complex numbers is a little bit different. To multiply complex numbers, we multiply as though they are binomials and then use the property I squared equals negative 1 to simplify. So let's take a look at these problems. So first up, we have 3 times 3i times 2 minus I. So we're going to distribute that 3i. So we're going to have 3i times 2 minus 3i times I. 3i times 2 is going to give me 6i. 3 times 2 is 6, and then that I stays attached. Minus 3 times I squared. 6i stays, minus 3. I squared we know to be negative 1. So we're going to have 6i plus 3. And that will be our final answer, except for usually we see the imaginary part written second. So we want our answer to be in the form of a complex number, 3 plus 6i. Okay, next up we have 2 minus 5i times 4 plus I. So this is where we have a binomial times a binomial, and we want to go ahead and FOIL it out. So 2 times 4 is 8. 2 times I is going to be 2i. Negative 5i times 4 is going to be minus 20i, and then negative 5i times I is going to be minus 5i squared. So then we get 8 plus 2i minus 20i. We can combine like terms in the middle here. So we're going to have 8 minus 18i. And then I squared is -1, so we're gonna have -5 times -1. So 8 minus 18i plus 5. And then 8 plus 5 we know to be 13. 8, 9, 10, 11, 12, 13. Yeah. So we're gonna get 13 minus 18i. So nothing too complex. It just kind of relies on things that you might have forgotten. So 2 minus I quantity squared is going to be equal to 2 minus I times 2 minus I, which is going to have to be FOILed again. 2 times 2 is 4, minus 2I minus 2I plus I squared. So that's going to be 4 minus 4I plus -1. 4 minus 4i minus 1. 4 minus 1 is 3, so we're going to get 3 minus 4i. Nothing too bad there. All right, next part is dividing complex numbers. The complex numbers a plus bi and a minus bi are called complex conjugates of each other. And a plus bi times a minus bi equals a squared minus b squared. So this kind of gets back to that idea that we talked about back when we were rationalizing, which was multiplying by the conjugate. So now that we're dealing with complex numbers, the conjugate's the same thing, like really the exact same binomial with the sign flipped in the middle. But they are called complex conjugates now because we are dealing with complex numbers. And we use these complex conjugates to divide by a complex number. So, for example, number 1, we have 2 plus I divided by 1 minus I. And so what we are going to do is we are going to multiply the numerator and denominator by the complex conjugate of 1 minus I to eliminate the imaginary number in the denominator. So the complex conjugate of my denominator is going to be 1 plus I. So I'm going to have 1 plus I. And then let's look at my denominator first. So I have 1 minus I times 1 plus I. And so I know that a minus b times a plus b equals a squared minus b squared. So my a in this case is 1, my b in this case is I. So 1 plus I times 1 minus I is going to be 1 squared minus I squared. 1 squared is 1. We know I squared is -1, so that's going to be 1 minus -1. So 1 plus 1, so 2. So my denominator is going to be 2. And then my numerator, I'm going to have to FOIL out. So I have 2 plus I times 1 plus I. So 2 times 1 is 2 plus 2I plus I plus I squared. So that's going to be 2 plus 3I minus 1. So 2 minus 1 is 1. So it's going to be 1 plus 3I in my numerator. So I'm going to get 1 plus 3I over 2. And you could also write that as equal to 1/2 plus 3/2 I. Those are equivalent statements, so your answer could be in either form. Okay, so dividing just relies on using that property right here, the difference of squares, which has really come into handy for us, and then just remembering how to FOIL these complex numbers. Let's do another example. So we have 7 over 3i, and again, we want to multiply by the complex conjugate of our numerator, or excuse me, of our denominator. So we know that our denominator is 3i, so the complex conjugate of 3i is going to be times -3i. Again, the word conjugate just kind of indicates to you, oh, signful. Okay, so then 7 times -3 is going to be -21. I in my numerator, and then in my denominator I have 3 times -3, which is -9 times I squared. I know that I squared is -1, so I'm going to have -21I over -9 times -1, which is going to be equal to -21I over 9. -21 over 9 simplifies a little bit to -7I over 3. And that is my final answer. And if I wanted that written in the form of a complex number, I would have 0 minus 7/3 I, right? Because complex number, again, has to be in the form of a plus bi or a minus bi. So if I don't have an a, it would be 0. And then part 5 is finding powers of I. So we can use the fact that I squared equals -1 to find higher powers of I. So for instance, I cubed, we could break into I squared times I. We know that I squared is -1, so -1 times I would be -I. Same thing with I to the 4th, I to the 5th, and I to the 6th. And so if we continue, we might notice that there's a pattern generated. So I want you guys to take a look at what I have written out here, see if you can pick up on the pattern, and we will talk about that more in class time. And on the homework, there should be a couple of problems where you're going to need to use the pattern to try and figure out a higher power of odd. So I want to see if you can put that pattern together and figure it out. If not, no worries, we'll talk about it in class. But yeah, thanks for watching, guys. Have a great day.